Rational root test or rational zero theorem is used to find the roots of a polynomial with degrees bigger than 2. So if we have a function with a degree of 2 or less than 2, which is easy, but if it is up to the degree of 2, we use the quadratic equation to find the roots. But if we have a function with the degrees bigger than 2, let's say x to the 5 plus 4x to the 4 plus and so forth, in this case, we cannot use the quadratic equation to find the roots. So we need to use the rational root test, which states that if we have a function of f of x in this form with a n x to the n plus a n minus 1 x to the n minus 1 plus so forth, and the last two terms are going to be a1 x plus a0, which is a constant. In this case, if that's our function that's our polynomial, then the possible, that's important, possible rational roots. The possible roots are going to be equal to p over q, where p are all the factors of a0. So the constant in our polynomial, all the factors of that divided by all the factors of a n, which is the highest coefficient that we have, the coefficient of the highest degree of x. So, and then we do the division, we get the possible roots, and from there we do the other test to find the actual roots of the function. So let's say if we have the polynomial f of x is equal to 2x to the fourth plus x to the third minus 17x squared plus 4x plus 6. So in order to find the possible roots, we do p over q. And then in the numerator, we are going to have the factors of 6. So the factors of 6 are 1, 2, 3, and 6. The highest degree coefficient is 2, so we have 1 and 2. And then we do the division. So we do 1 over 1 and 2, 2 over. So here we get, these are the values that we will get. So plus or negative 1 over 1, negative 1 over 2, and so forth. So we do the fractions and we get all the possible roots here from here. And then we gotta do some elimination of the duplicates because we are gonna have duplicates. So 6 over 2 is gonna give us 3 over 1. So we have multiple duplicates, and then at the end, if we do the we write them out, eliminate the duplicates, we are gonna get 1, negative 1, 2, negative 2, 3, and negative 3, 6, and negative 6. Then we have 1/2, negative 1/2, 3 over 2, negative 3 over 2. So these are going to be all the possible roots for this polynomial that we had here, 2x to the fourth and so on. Now, if leading coefficient is equal to 1. Therefore, the possible roots is going to be just the factors of the constant term. Now let's jump into one example and see how we can use the rational root test to find the possible roots and then use the possible roots to find the actual roots of that polynomial. For our first example, let's say that we have the function or the polynomial of px is equal to 3x to the third minus 4x squared minus 17x plus 6. The first step of finding the actual roots is finding the possible roots. The possible roots, as we said, is equal to p over q, which here p are the factors of 6, 1, 2, 3, and 6. And for the leading coefficient, we have 1 and 3. Now we do the division here, dividing the values. So we get plus and minus 1, 1 divided by 1. Then we have plus and minus 1 over 3. Then we have 2 over 1, which gives us 2. Then 2 over 3. Then 3 over 1. 3 over 3 gives us a 1. We already had the 1, so we skip it. Then we have 6 over 1, 6, and then we have 6 over 3 gives us a 2, and we have already had it. So we have 6 terms multiplied by 2 for plus and minus, so 12 possible roots. The second step is to find the actual factors, the actual roots of the polynomial. And how do we do that? From the factor theorem and the remainder theorem, we know that if we have the function of p and we plug in the value of a, and if the result is equal to 0, that means that a is a factor of the function. So here we have 12 values of a that we need to plug in to our function p and see if it equals to 0 or not. If it does, that means that value is a factor, is truly a factor of the polynomial. So here I have a table already done with the values of our the possible roots that we have found. So 12 of them, and only 3 of them gives a result of 0. So those are the actual roots. So the actual roots are 1/3, -2, and 3. So these 3 values are the actual roots of this polynomial. Right after this, we will do another example that we will find the actual roots and also do some factoring to see how it plays out. For our next example, let's say that we have the polynomial g of x is equal to 4x to the fifth minus 12x to the fourth plus 5x to the third plus 8x squared minus 3x minus 2. And we want to find the actual roots of this polynomial. So let's start with the first step, p over q. So it's going to be a little bit easier here. We have less, so we have 1 and 2 as our constant is the 2, and the leading coefficient is a 4, so plus minus 1, 2, and 4. So we do the same thing that we did before, we get these values, plus or minus 1 over 4, plus or minus 1 over 2, plus or minus 1, plus or minus 2. So these 8 terms, 8 values are the possible roots of the polynomial. So the next one, we plug in these 8 into the g of x as x value, and we find that only we will have 3 actual roots. So those are going to be g of negative 1/2. That if we do it, it's going to be 4 times negative 1/2 to the 5th minus 12 negative 1/2 to the 4 plus 5 negative 1/2 to the 3rd plus 8 negative 1/2 to the 2 minus 3 negative 1/2 minus 2, and simplify, we get 0. The same result of 0, we will get it. This is going to be 0, and also g of 2 is going to be 0. So negative 1/2, 1, and 2 are the 3 actual roots. So the real roots are negative 1/2, 1, and 2. That's good. But if you notice, we have a degree of 5. So we are going to have actually 5 roots for that polynomial. But we found only 3, which are the real roots. That means it's going to have 2 irrational roots, possibly irrational roots. So the next thing that we need to do is first we factor out these roots from the polynomial, and then we see it's going to be left with a second degree function, and from that we can use the quadratic equation to find the other 2 roots. Let's do that. So we start with x plus 1/2 and see what we get. So we do the long division of g of x divided by x minus negative 1/2, which becomes x plus 1/2. And if we do the division, we gotta use long division or synthetic division, whichever you feel comfortable, and then we get 4x to the 4th minus 14x to the 3rd plus 12x to the 2nd plus 2x minus 4. Now that's the first step that we did. Now the second step is that we divide this one by x minus 1, and then we get one step closer to the final answer, so x minus 1, and then the remainder of that would be, or the quotient will be, the remainder is going to be 0, so the quotient is going to be 4x to the 3rd minus 10x squared plus 2x plus 4. Now we divide this one by x minus 2, so one step at a time we get closer to the final polynomial that we are looking for. And when we do that, we are going to be left with x squared minus 2x minus 2. Now, we use all the 3 factors all the three roots that we had, we factored them out, and we are left with that polynomial. So this polynomial for x squared minus 2x minus 2, we need to find the two roots that this one is going to give us. So what I'm going to do first, I'm going to divide the whole thing by 2 to get a simpler polynomial, minus x minus 1. Now, from here, we know how to use the quadratic equation. So the quadratic equation is negative b plus or minus b squared minus 4ac, and then the whole thing divided by 2a. We plug in the values a, b, c. So we plug in the values and let's see what we get. Plus or minus b squared negative 1 squared minus 4 times a, which is a 2, times c, which is a negative 1, divided by 2 times a, which is that. So now if we do the simplification, what we are going to get is plus 1 plus or minus root value of 10 over 4. So we have here two irrational roots, one plus root 10 over 4 and one minus root 10 over 4. So we got two roots here, three real roots here, and it gives us the total of 5 roots for the polynomial. So not always when we do we use the possible roots to get and we use the f of x or g of x is and we plug in the values of the roots, the possible roots, to find the actual root. Remember, this is the rational root test, so it's going to give us the rational roots. When we find it, if we find that the rational roots are less than the highest degree of the polynomial, then we need to do the factoring, the whatever the polynomial is left, which most likely it's going to be a second degree. We use the quadratic equation to find the other two roots.